In this video, we're going to be covering the second derivative test. The second derivative test, like the first, also finds local maximum and minimums. There is one issue with the second derivative test, and if you notice part C here where it says, if the second derivative is equal to 0, then the test is inconclusive and you must use the first derivative test to determine local extrema. So, other than that, everything else on this is going to be pretty well straightforward. So, f of x in this case is equal to 5x to the power of 3 minus 3x to the power of 5. My first step is to take the derivative, 15x squared minus 15x to the fourth. In that case, again, to find potential locations of max and min, I need to find my critical points of this function, again, where the first derivative is equal to 0, or the first derivative does not exist. But again, one more time, this being a polynomial function, we don't have that second case. But I always want to keep considering it just so I don't forget it. So if I set this thing equal to 0 and factor, I'm going to have 15x squared factored out, giving me 1 minus x squared. This one here is going to give me x0. Technically, it's going to happen twice at that location, but I'm just going to go ahead and leave it there as x equals 0. This one here, you'll notice if I add the x squared to both sides, again setting it equal to 0, I'll end up having x equals plus or minus 1. So I have three different critical points for this function. Now, in the first derivative test, you'd have to create yourself a number line and plug everything in. But the second derivative test is a little bit more efficient if we can easily take the second derivative and if we don't get 0 when we plug these numbers in. So when I take the second derivative test, it's nothing more than me taking the derivative of the first function, giving me 2 times 15, which is 30x, minus 4 times 15, which is 60, x to the power of 3. Now with this second derivative, my goal is to figure out what is the second derivative at each one of those critical points. So I'm going to go ahead in the second derivative and plug these numbers in. Now, if I plug in 0 to the second derivative, you'll notice I get back 0, which means inconclusive. That's unfortunate for that case, but at least I know that I'm going to have to use the first derivative test on 0. At 1, when I plug in 1, I get 30 minus 60, which ends up being a negative 30. Again, the number itself doesn't matter. It's just the fact that it is negative. Now, let's talk about what this means. At the value of 1, the function's second derivative is negative, which means that at the value of 1, which could be a location where there's a max or a min, we should see something that is a concave down function. Well, it could do concave up everywhere else and concave down other places, but at that location, that's the point at the top of that loop. So because the second derivative is negative, we have a concave down situation. That right there would be my so-called local maximum. So I can say by the second derivative test, at x equals 1, there is a local maximum. And it has a value of me simply plugging 1 into the original function. Now again, don't confuse this. This tests whether or not the value happens to have a max or a min at it, but I need to figure out what the max or min is by plugging in 1 to the original function. So by doing so, I'm going to have 5 times 1 cubed minus 3 times 1 to the 5th, which in this case is simply just 2. So I'm going to have a local maximum at the value of a y value of 2. It's the occurrence at x equals 1. So I'm going to do the same thing with this negative one. I'm going to plug it back into here, giving me a negative 30 minus plus a 60, which gives me a positive value. And therefore, again, based on that information, I have a concave up situation. But a concave up situation provides me with a location right here where I can guarantee that is going to give me a local minimum. So I'm going to have a local minimum at x equals negative 1. And again, the value of that minimum is f of negative 1, which gives me, in this case, it'll be negative 5 and a positive 3, so it ends up being a negative 2. So now those two are guaranteed solutions based on the second derivative test. Now how do I deal with the 0 for the inconclusive situation? Well, you'll notice if I attempt to go ahead and deal with that using this rule right here, my number line test, I'm going to have 0 as a point, I'm going to have negative 1 as a point, I'm going to have 1 as a point. For my test values, now I'm not going to do this whole table because I don't need to work with 1 and negative 1 anymore, but I need to work with 0. So I need to know what's happening before it and what's happening after it. In that case, the test values I'm going to pick is a negative 0.5 and a 0.5, and those two things are going to go into the first derivative in here. again, because I'm using the first derivative test to test 0. So now in this case, if I go ahead and do that, now keep in mind, this problem didn't ask me to find it using the first derivative test. It said use it using the second derivative test, which part of the second derivative test is to use the first if the second was inconclusive. So when I plug in negative 0.5 into here, I'm going to get a 1 minus a number, so that's going to be a positive value. And out here, this is going to be a positive value. So this is positive and this is positive, no matter what values I pick. So it'll be positive, which is increasing, and positive, which is increasing, which means that this location is not a max, nor is it a min. It actually ends up being something like this in terms of the graph. Okay, so that location would happen, give or take, right about there. What we call that point is actually more or less an inflection point. We'll work with that again in other videos, but in this particular situation, that is an inflection point, which allows me to identify that the concavity changes, but that the maximum and minimum will not occur there.